Hi, welcome to MATH336. This is section 2.1. We're starting chapter 2 today, and we're going to get in now to second order differential equations. And in particular, we're going to start with the second order linear equations. Okay. So this is a general form of a second order linear differential equation. So you see that it's linear in the dependent variable, which is y. So y is the dependent variable. This equation is linear in y and in the derivatives of y, so y prime and y double prime. So now that we're doing second order differential equations, we're going to be looking at differential equations that involve the second derivative as well as the first derivative. Okay, so this is really a completely different type of differential equation than what we're used to. And I'd like to start off just by showing you an example of a differential equation that is of this form. And we're going to get into this into more detail later, but it's nice to see it now. So we're going to be looking at like mechanical vibrations. I forget what section, it's like 2.6 or something. We're going to be looking at mechanical vibrations that are of this form where we have some kind of a mass that's attached to a spring here. And on the other side, it's attached to a dashpot, which is kind of a, it's, for example, on doors that have the device that makes sure that it closes slowly. That is an example of a dashpot. The dashpot we can also think of this as just being friction as well. So it's a type of friction. So without this dashpot, then this mass would just oscillate back and forth forever. But the dashpot sort of damps down on those vibrations, and so it'll cause the mass to eventually stop vibrating. So so what are we measuring here? So imagine that when this mass is at rest, so right now the string is stretched this direction. If the spring isn't stretched, then the mass would be sitting right here. But we've now moved the mass in this direction, so the spring is stretched, which means the spring is providing a force in that direction. And at the same time, the dashpot is providing a force in this direction as well. So it's sort of preventing the spring from pulling this mass back very quickly. So we model the spring force as being some multiple times the displacement, right? So here x is being displaced by a positive amount, and this negative kx means that the spring is pulling it back to the left. So that's our spring force. And then the dashpot is related to the velocity of the function, right? So you know, with these devices on doors, if you just sort of are holding it open, you don't feel a force from that that device. But you do if you like try to push it open faster than it wants to be pushed open, or if you try to pull the door closed faster than it would like to close, then you definitely feel the force from this dashpot. So that's why this dashpot force is it's going to be related to the velocity. So the more velocity that you're applying to this mass, the stronger the force is, and it's in, again, the opposite direction as the velocity. So positive velocity means that it's moving to the right, and negative velocity means that it's moving to the left. So this is always going to be a force that's in the opposite direction. Okay, so then we just use this well-known equation, force is equal to mass times acceleration. And what is the total force? We just add up the force from the spring and the force from the dashpot, and that is going to be equal to m times the second derivative of x. And when you rewrite this equation here by substituting in this term here and this term here, and then moving everything to one side of the equation, we're going to get this very nice equation here. So you can see this is of the form of this, this general form of second order linear differential equation. The only difference is these coefficients here are just constants. Although I guess there's no reason why they couldn't also be a function of time. Okay, so this is when you have a differential equation like this where the right-hand side is 0, then we call this a homogeneous equation. So not to be confused, we also used homogeneous for in the first chapter for a different reason. So still keep that definition of homogeneous in mind, but in this chapter when we talk about homogeneous, we mean a differential equation where the right-hand side is 0. Now, if we had an external force on the system, like maybe we have a force that's acting on this mass that's kind of like pushing it back and forth like this. Maybe it's like an earthquake or something that's causing an external force. Then you can put that external force on the right-hand side. And when you do that, you get a non-homogeneous equation. So this distinction between homogeneous and non-homogeneous is going to be very important. It's key to how we are going to solve these second order differential equations. We're first going to always look at the homogeneous version of it, and then once we have the solutions for this, then we will take the solutions that we get from this and we will extend them so that they are solutions of this. So we'll learn about this later, but you get kind of like a general formula here, and then you get a particular solution here, and you just add those two. So you take the general solution from this, you add it to a particular solution of this, and that gives you your complete solution of this non-homogeneous equation. Okay, so now that I've mentioned how important these homogeneous equations are, let's have a look at them in more detail. So a homogeneous equation has a really nice property that if you have two solutions of the homogeneous equation, then you can combine them to get another solution for the homogeneous equation. And how do we combine them? Well, we do what's called a linear combination. So this is a linear combination of two solutions, y1 and y2. So we take a constant, c1, and we multiply that with y1. And we take a constant, c2, and we multiply that to y2, and then we add them. So you could think about this as like taking a certain amount of y1, a certain amount of y2, where the amount is given by these coefficients here, and then just combining those together. It's kind of like a recipe, take a certain amount of flour, take a certain amount of sugar, and then mix them together. So that's a good way to think of this. So obviously we see why we're using the word combination, because we're combining these two functions together. But it's in particular a linear combination because we're not combining them like by multiplying them or anything like that. We're combining them in this looks very much like a linear expression, just like we saw of the linear expression of the differential equation. Okay, so that's a linear combination. It's kind of like a recipe for y given the ingredients of y1 and y2. So that is also going to be a solution. So that is the sort of the key property of these homogeneous equations. And we'll do an example of this, and we'll see that indeed this is true. Okay, so take, for example, this differential equation here. So maybe I'll highlight this. So there's our differential equation, and we have now with these second order differential equations, we actually need two initial conditions. We need to know what is the initial position, and we need to know what the initial velocity is, right? And if you think about this, this makes a lot of sense when we're talking about like the dropping a ball or jumping out of an airplane. You need to know with a parachute, you need to know what is our initial height and what is our initial velocity, right? So you need those two things to be able to solve the problem. And this in general is true for second order differential equations. And we'll see how we use both of these conditions to solve the problem. So we're going to start by showing that, that these two functions here, this one and this one, we're going to show that these are both solutions of this differential equation. And then we're going to combine them as we'll do this linear combination of those two solutions. And we'll show that indeed this is going to be a solution as well. After we do that, then we're going to use these initial conditions to determine the C1 and the C2. Okay, so we'll see that both of these conditions are necessary to be able to determine these. And then that's it. And then we'll finally have our solution for this initial value problem. Okay, so let's get started on this. Let's see. So the first thing we want to do is show that y1 is a solution. So let me just write down the differential equation again. So y double prime plus 2y prime plus y equals 0. Okay, and we're going to take y1 equal to e to the negative x. Yeah. Okay, so we want to substitute this into this equation. So we'll need to take the derivative twice. So once we get this, and then the second derivative will give us this. Okay, so there's our three terms that we need. So now let's substitute them into this equation. So we'll have y1 double prime plus 2y1 plus y1 prime plus y1. And what do we get? This will be e to the negative x plus 2 times negative e to the negative x plus e to the negative x. And yeah, so this is going to give us 1, 2. So we have 2e to the negative x, and we have negative 2e to the negative x. So that will cancel, and we will be left with 0. So indeed, y1 is a solution. So now let's look at y2. This is x e to the negative x. y2 prime is going to be the derivative of the first. Well, I guess we'll do first times the derivative of the second. So that'll give us that, and then we'll do the derivative of the first times the second, like that. Okay. And now we'll do the second derivative. The first times the derivative of the second. So that's just going to cancel this minus sign. So I'll just move that over. And then plus the derivative of the first, which is minus 1, times the second. And then we also take the derivative of e to the negative x. Okay. So let's combine these now and see that it satisfies this differential equation. Oops, y2 prime plus y2. So y2, I'm going to simplify this. This is going to be, let's see, I guess I could do x minus 2 e to the negative x. And then plus 2, and actually this one I can do 1 minus x times e to the negative x. And y2 itself is plus x e to the negative x. Okay, so what do we get? So we have a negative 2 e to the negative x, and we have a 2 e to the negative x, so that will cancel with that. And then we're left with x e to the negative x plus another x e to the negative x. So those will combine to be 2x e to the negative x. So maybe I'll just write that out here. 2x e to the negative x. And then we have another 2 negative x e to the negative x over here. So 2x e to the negative x. And those cancel and give us 0. So y2 is also a solution of this differential equation. Okay, so now we want to show that if we take y equals c1 y1 plus c2 y2, that this is a solution of the differential equation as well. So let's see how this works. So let's take the derivative of this. This will be c1 y1 prime plus c2 y2 prime, and y double prime equals c1 y1 double prime plus c2 y2 double prime. Okay, so let's take this and substitute it into the differential equation. So y1 double prime is c1 y1 double prime plus c2 y2 double prime. So that's the first term, plus 2 times c1 y1 prime plus c2 y2 prime plus c1 y1 plus c2 y2. Okay, so what do we get? I'm gonna move this over here. Well, maybe let's see. How do I want to do this? Let's put that there. Let's see. So that implies that, okay, so let's combine the y1 terms here, here, and here, and we'll combine the y2 terms together. So the y1 terms are going to be c1 y1 double prime plus 2c1 y1 prime plus c1 y1. So it's just reorganizing. And then we have c1 y2 double prime plus c2 2c2 y2 prime plus c2 y2. Okay. I can factor out a c1. So there's a c1 here. I'll factor that out. So that'll come out there. And there's also, did I make a mistake? I think I did make a mistake. So here, it's supposed to be c2 y2 double prime. So that should be a 2. So now I can also factor a c2 out. So there's a c2, 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 and I'll factor that out. Okay, so what do we get? c1 times y1 double prime plus 2, oh, that c1's coming out. Plus that, okay. C2, y2 double prime plus 2y2 prime plus y2. Okay, I'm just going to insert a page into this book. Okay, page inserted. All right, so we're getting there. Maybe let's make some more room here. I'll just move this stuff over here. Maybe I'll just leave it. I'll just leave it. Maybe I'll copy this down. That would be good. Copy and put that right there. Okay. So that implies we get this, and therefore so what is this actually? We know what this is. I think we showed that this is equal to 0, right? So let's check that. Right here, yeah, that is equal to 0. So that we can put 0 there. And what about this one? That one we also showed is equal to 0. That is right here. So that is equal to 0. So we can substitute 0 in for those. So we get C1 times 0 plus C2 times 0, and that is equal to 0. So we get, we showed what we wanted to show. So that means that y, which is this linear combination of y1 and y2, it also is a solution of this differential equation. Okay. So, and hopefully you see that this will work in general. So this is why linear combinations of solutions for homogeneous equations give us a solution of the homogeneous equation. It's because this type of calculation will always work for any homogeneous linear equation. Okay, so now what do we do? So now we want to look at these initial conditions. So let me copy that, and we will see how we use them to determine these coefficients, C1 and C2. So here are the initial conditions. So maybe I'll just write them down here. So we have y0 equals 2, and then we'll figure out what that means. And we have y prime of 0 equals -1, and we'll work that out. Okay, so let's just get rid of this, and let's see. Maybe it would be a good idea to write out what y is. So y is equal to c1 e to the negative x plus c2 x e to the negative x. So this is our, in fact, it's a general solution for this differential equation. Okay, so we substitute 0 in there. So we get c1 e to the 0, which is 1, plus c2 times 0 times e to the 0. So that's 1, and that will be equal to 2. Now what about this y prime of 0? So I guess it would help to actually have y prime. So maybe let's just write down the formula for y prime. That'll make our lives a little bit easier. So y prime is equal to -c1 e to the negative x plus c2, and then this is going to actually be y2 prime, which I have a formula for that up here already. It's right here. So this is y2 prime. So I'll just copy that and bring that down here. So I'll paste that right there and then put parentheses around it. So there's our y1 prime. So we can now substitute 0 into that. and see what we get. So we'll have negative C1 times e to the negative 0, that's 1, plus C2 times 0 times 1 plus 1. And that is equal to negative 1 from this over here. Okay, let's simplify these equations. So therefore, we have C1 is equal to 2, and we have negative C1 plus C2 is equal to negative 1. So what we have here is a system of linear equations. Let's see, did I do that right? Yes, I think that's okay. So here's a system of linear equations. Now this one is especially easy because one technique you can use for solving a system of linear equations is to take one equation and solve it for one of the variables and then substitute it into the other equation. And that's how you can get the values for both variables. This one is especially easy because we already know that C1 is 2. So we're just going to substitute 2 into here. And what do we get? So therefore we get C1 is 2, and we have negative 2 plus C2 is negative 1. So that tells us that C2 is going to be 1. So there's our solutions. So right there, maybe I'll do it in orange. There's our C1 and C2. So what is our solution then? So therefore, the solution of the initial value problem is y equals 2 e to the negative x plus 1 times x e to the negative x. So that is our final solution. So this function here is going to satisfy the differential equation, and it will satisfy the initial conditions, the initial position and the initial velocity. And that is our solution to the initial value problem. All right. Good. Okay, so an important idea when we're taking two solutions of a differential equation and then combining them as a linear combination. So here's that linear combination again, right there. So we're going to form this linear combination, and a really important property for these functions to have is that they are that they're not redundant ingredients. So you imagine if I was to take, you know, C1 or like some amount of like sugar. So say that's my initial ingredient is some amount of sugar, and then I have some amount of sugar again, right? So I don't really need to have sugar in both places, right? That's redundant, right? So I don't want this and this to be like basically the same thing. So let's see what this means algebraically. So imagine that you know, like y1 is some ingredient and y2 is just a multiple of that ingredient. So if we substitute this into this linear combination, then what we end up getting is that y is just, well, let me go through this carefully, I guess. So I substitute this in here. Maybe I'll put parentheses around that to really emphasize, make it a little bit easier to see. So it's C2 times C1, CY1. And if you factor out this common y1 term, then we end up getting just a constant times y1. So then why did we introduce y2? You know, it it doesn't make any sense. In fact, I can just replace this with another constant and we just get y is equal to C3y1. So really y2 doesn't contribute anything. So y2 is redundant. Oops, it's a redundant function. So it's not needed, right? And when this happens, we say that y1 and y2 are linearly dependent. So when we detect this redundancy, then we say that they're linearly dependent. And the test for this is to see if there exists C1 and C2 not both 0, such that this linear combination is equal to 0. So that's just a general way to check if we have this redundancy amongst our functions. Let's see. And the reason why we especially like this definition is because it generalizes nicely when you have like 3 or 4 or 5 functions. So that's why this is kind of the preferred way to think about linear dependence. And it's also a very easy thing to check, as we'll see in the examples. So in order for us to be able to satisfy the initial conditions, the property that we need is to have to avoid this redundancy, and that property is called linearly independent. So we need to have 2 linearly independent functions, y1 and y2, to avoid redundancy and satisfy the initial conditions, right? So if you don't have 2 linearly independent functions, you might not be able to satisfy the initial conditions. And the way that we can define this linearly independent is just the opposite of this definition here. It says that if we have this linear combination of functions equals 0, then that implies that C1 and C2 have to both be 0. So, and we'll see this in the examples. Okay. So let's start out with this example. Determine if the functions are linearly dependent or linearly independent on the real line. So that means for all x, all real values of x. Okay, so let's use this idea that we're going to take some C1 times the first function plus C2 times the second function, and we'll set that equal to 0. And this should be true for all x. So let's substitute the formulas for these functions in here. Let's see, absolute value equals 0. And again, this has to be true for all x. So we can substitute some values in. Let me just move this. I need a little bit more room. There we go. Okay, so we can now substitute values in here and see if we can solve this equation for C1 and C2. So let's just try x equals 1. So this has to be true for all x, so it has to be true for x equals 1. So if we substitute x equals 1 in, then we get C1 times 1 cubed, so that's just 1, plus C2 times 1 squared times the absolute value of 1, so that's 1 times 1, and that will give us 0. So that means that we need to have C1 plus C2 equal to 0. Okay, so that was rather successful. I feel like now trying -1, another obvious thing to try is like I don't know, 2 or something, but I think we'll end up getting the same thing here. Let me just put a box around this because that is important right there. If I put 0 in, that's not going to help because that's just going to be 0 plus 0 equals 0. That doesn't give us any information. So that's why I'm thinking about choosing something negative, especially because of this absolute value. That the negative may give us more information. So we'll have C1 times -1 cubed. Maybe I'll actually put these in squared. Let's see. I'll actually put all this stuff in. So absolute value of 1. Okay. Cubed plus C2 times -1 squared times absolute value of -1 equals 0. Okay, what do we get now? Well, -1 cubed, that's -1. So we'll get negative C1. -1 squared is 1. Absolute value of -1 is 1. So this will give us C2 equals 0. Okay, so there's our second equation. And now you see again we have a system of linear equations. We have two linear equations in two variables. So we can solve these two equations to get the solution. Okay, so let's see. I think I need to make a little bit more room here again. Okay, so let's see. Well, what can we do? So I guess let's start with the second equation here, and we'll solve that for, I don't know, C2, I guess. So we'll get that C2 is equal to C1, right? So I'll just add C1 to both sides of this equation. So that'll move this over here. So C2 is equal to C1. And then I'll substitute that into the first equation. I'll get C1 plus C2, which is C1, is equal to 0. And what does that tell us? Let's see. So that tells us that 2C1 is equal to 0. And we still have this. And then I think that tells us, so this one now tells us that C1 has to be 0. And then that tells us that C2 has to be 0. So yeah, this clearly tells us that C1 and C2 have to be 0. So therefore, f of x and g of x are linearly independent, right? So these are not redundant in any way. So there's our solution to this system of linear equations. Okay, great. So those are linearly independent. Now there's another way that we could actually have determined that C1 and C2 are 0, and that's using something called the determinant. So why don't I show you that? Because that's actually a pretty nice trick, which saves us some time. So we're going to look at the determinant of the matrix of coefficients of this linear system. So let's do that right now. Let's see, I'm going to move this down here. So this is probably familiar. You've probably seen this before. So let's just say another, maybe I would say it's an easier method. So here, and easier method using the determinant. So here's an easier method. So we have this C1 plus C2 equals 0 and negative C1 plus C2 equals 0. So there is our linear system. And we're interested in the coefficient matrix of this linear system. So what is that? So the determinant of the matrix of coefficients is, and typically this is written with vertical bars, so the matrix is 1, 1, negative 1, 1. So that's the determinant of that matrix. And maybe I'll write the general formula up here. So you've probably seen this before. If you have a determinant of the matrix A, B, C, D, then this is going to be A times D minus C times B. Or maybe, I forget which way, anyway, it doesn't matter so much. So A times D minus, let's do C times B, or B times C, whichever you prefer. So you probably remember this formula. Let me just let's put a nice box around it. So that's the formula for a 2 by 2 determinant. So let's apply this formula here. It is going to be 1 times 1 minus 1 times 1. So we'll get 1 times 1 minus 1 times 1. And this is going to give us 2. So if you recall, because the determinant of this matrix of coefficients is 2, and in particular it's not 0, so that implies that C1 and C2 are both 0. So in more details, what it tells us is that there is exactly one solution to this linear system. That's what having a non-zero determinant tells us. It tells us that there is exactly one solution to this linear system. And clearly, if I put zeros here, that's true. And if I put zeros here, that's true. So 0, 0 is a solution. And now we know that it is the only solution. So I just find this to be a lot easier than what we did above. You just simply do this determinant calculation, and you immediately find out if there is only the 0 solution or if there's another solution. Okay, so we'll use that method on this next one, because this next one is going to be somewhat more difficult. So that's the idea. So therefore, we have linearly independent f of x and g of x. So that's sort of the another way to do it, an easier way. All right, so let's try that with this one. So again, we start off by forming this linear combination and setting that to 0. And this should be true for all x. So what do we get? So C1 times 2 cosine x plus 3 sine x plus C2 times 3 cos x minus 2 sine x is equal to 0. That is equal to 0. Okay. And let's see. So I'm going to suggest again, I guess we could plug values in, or I mean, we could just rearrange and, combine the cosine terms. Yeah, maybe let's do that first. So let's rearrange this. So we have the cosine, so we have 2c1 plus 3c2 times cosine x plus 3c1 minus 2c2 sine x is equal to 0. And again, remember, this is true for all x, right? So we can now substitute in different values of x into this. So I think I can substitute a value in so that, this is not 0 and this one is 0. So we know that sine of x is going to be 0 if I plug in like 0, or let's see, 0. What else is there? Sine of pi is going to be 0. Sine of 2 pi, that'll be 0 as well. So let's do that. Let's see. 1 second. Okay. All right, so let's try x equals 0. So then cosine of 0 is 1. So that'll be 1. And sine of 0 is 0. So that means that we have 2c1 plus 3c2 is equal to 0. Okay, perfect. Now, what can we plug in to get cosine to be 0? So cosine of pi over 2, that's 0. And sine of pi over 2 is 1. So let's plug in pi over 2. So x equals pi over 2. And we will get 2c1 plus 3c2 times 0 plus 3c1 minus 2c2 times 1. And so therefore we get 3c1 minus 2c2 is equal to 0. Okay, so now if we were to do the first method with these two equations, try to solve this 2 by 2 linear system, 2 variables and 2 equations. So if we were to try to solve this, it would not be fun. It would be a lot of algebra, and so let's use the determinant trick. So the determinant trick is very simple calculation: 2 times negative 2 minus 3 times 3, and if that's not 0, then we know that there's only one solution to this linear system. So let's do that. So what is the determinant? So the determinant of this linear system, 2, 3, 3, minus 2. This is going to be 2 times negative 2 minus 3 times 3. And what do we get? So that'll be negative 4 minus 9, so negative 13. That is not 0. So therefore, C1 and C2 have to be 0. That's the only solution to that linear system. You see how easy that is? I really love using determinants for this type of calculation. So they have to be 0, and therefore f of x and g of x are linearly independent. All right, so that is it. And if this determinant was 0, then we know that those functions have to be linearly dependent. So that is the idea. Okay, great. Next. Okay. So here is the reason why we're so interested in having 2 linearly independent solutions. It's because if we have a differential equation of this form here, then this guy right there is a general solution of the differential equation. That means that any solution of this differential equation can be written in this form. And that is only possible if we have two linearly independent solutions of this equation. So that's why it's so important to get two linearly independent solutions. Now, once we have our general solution to the differential equation, we want to then determine the value of C1 and C2 so that it satisfies our initial conditions, right? So our initial position and initial velocity, right? So we want to satisfy these two initial conditions to find the values of C1 and C2. So we did this in the first example, if you recall. So what did we do in that example? Well, we took y of a equals b0, and we substituted a into this general solution up here, right? So we substituted a. So y of a, so that gives us c1 times y1 of a plus c2 times y2 of a, and that has to be equal to b0. So we get this equation here. Now, if we do the same thing for the other one, so we do y prime of a equals b1, and we know what y prime is. It's just going to be, y prime is equal to c1 times y1 prime plus c2 times y2 prime. So we just put primes here, right? So that gives us our formula for y prime. And that means that we have c1 times y1 prime of a plus c2 times y2 prime of a, that equals b1, right? So again, we have our 2x2 linear system, just like what we saw. I guess we've seen this now 3 times. In the first example, we had a simple 2x2 linear system, so we just kind of solved that directly. If you recall what that was, let's just go back and identify that. It was a while ago, so here it is right here. So this is our first 2x2 linear system that we're using to solve, to determine the values of C1 and C2 that satisfy the initial conditions. And it was very simple to solve, because we immediately had from the first equation, C1 is 2. And by the way, this type of linear system is called lower triangular because it has this lower triangular shape to the equations. Those are very easy to solve. So we just did C1 is equal to 2, and then we immediately got the value for C2 from the second equation by substituting. It's actually called forward substitution, that method for solving lower triangular matrices or a lower triangular system. And then, yeah, so that was what we did back there. And now we're just looking at this in general. And again, here is our linear system. Okay, so let's combine what we know from the first two examples. What we know is that this is the linear system we want to solve. That's what we saw from the first example. And then from the second example, we saw that the key to determining if we're guaranteed to have a solution to this system is by looking at the determinant of the coefficient matrix of this linear system. So this linear system has a solution for C1 and C2 if the following determinant is non-zero. So what is the matrix of coefficients? This is the coefficient for C1. This is the coefficient for C2. That in the second equation, those are the coefficients for C1 and C2. So that's going to be the entries of our 2x2 matrix. Okay, so let's look at that. So there it is right there. So there's our coefficients in the first equation. These are the coefficients in the second equation. And we want the determinant of this matrix. So what is that? So we just multiply this times this, and then we subtract this times this, and that gives us y1 of a times y2 prime of a minus y1 prime of a times y2 of a. So that's it. That's all we need to do to determine if there is a guaranteed solution for C1 and C2 given the initial conditions. And the key thing is, and we'll see this in a bit, that what we're interested in is when is this non-zero? Yeah, when is this non-zero? If this is non-zero, then we're good. And it turns out that if we have linear independence, then this thing is guaranteed to be non-zero. All right. So here's that formula again, just recalling something that you've seen. I'm sure everyone has seen 2x2 determinants before, but anyway, there's the formula for you to remember. Okay. So let's do an example where we actually determine we'll determine the coefficients C1 and C2 such that this linear combination satisfies the initial conditions, this one and this one. So this actually comes from a differential equation. These are two solutions to the same differential equation. We don't really need to know what it is, but if you're interested, I guess I could write it out. It does come from this example too. So the differential equation is going to be y prime minus 9y equals 0. So that's the differential equation if you're curious. But the important thing is that these are both solutions for the same differential equation. And then these are the initial position and initial velocity. Okay. So let's do this, and again we'll use this this idea of the determinant. Okay, so what do we need? So y is c1 e to the 3x plus c2 e to the negative 3x. And so therefore y prime is equal to 3c1 e to the 3x plus, oh no, it's minus actually, minus 3c2 e to the negative 3x. And what are our initial conditions? So we have y of 0, right? Y of 0 equals minus 1. So let's figure that out. Substitute 0, so c1 times e to the 0, that's 1, plus c2 times e to the negative 0, negative 3 times 0, that's also 1, and that equals negative 1. And then y prime of 0 is equal to 15. Okay, so let's see. So I have 3c1 times 0 minus 3c2 times 0, and that equals 15. Okay, let's simplify this again. Okay, just added a page to my notebook here. All right, so what do we get then? So we have c1 plus c2 is equal to negative 1, and 3c1 minus 3c2 equals 15. Now, We can use the determinant here again just to verify that we're guaranteed to have a unique solution to this linear system. So let's just check that quickly. So the determinant is 1, 1, 3, negative 3, and that is going to be 1 times negative 3 minus 3 times 1, and that gives us negative 6. So that's not 0. So therefore, there is a unique solution to the linear system. To this linear system. So this has a unique solution. So I guess what we could do, let's be kind of smart about it. Instead of solving for one and substituting into the other, that looks kind of bad. What I could do is multiply this equation by 3, and then I can add it to this equation, and that will cancel this term here. So let's do that. Maybe I'll just do it up here. So I can do 3c1 plus 3c2 equals negative 3. 3c1 minus 3c2 equals 15. I'm going to add them together. I get 6c1, and then this is just 0. And here we get 12. So that tells us that maybe I should move this down. Let's just move that down there, because I want to write it right here. So therefore, C1 is equal to 2. So there's our first value. And then let's just substitute that into the first equation. That looks easiest. So then we get 2 plus C2 is equal to negative 1. And so C2 is equal to negative 3. There it is. And because of our determinant calculation, we know that this is the only solution of this linear system. So there's a unique solution to this linear system, which is C1 equals 2 and C2 is equal to negative 3. So therefore, y is equal to 2e to the negative, oh no, that one's 3x. 2e to the 3x minus 3e to the negative 3x. So that is the solution to that differential equation that satisfies those two initial conditions. Okay. All right. So there, we just threw in an example into this discussion about what is this linear system? It's nice to see an example. What is this linear system? And why is it important to look at the determinant of this matrix? All right. So I guess we could have just directly formed this matrix and then calculated it. That would have been interesting too. Yeah, let's see. Let's just see what we get if we were to form this matrix and then take its determinant in this example. So let me undo this. So let's just also if we do y1, y2, y1 prime, y2 prime. I mean, I guess I could throw the a in there, but let's just leave it like this. So we'll just do it with the x. So what is this? So y1 is e to the 3x, y2 is e to the negative 3x, and this was 3e to the 3x, and negative 3e to the negative 3x. I guess what we're doing here is we're trying to decide if there's always a unique solution to the initial conditions or not. So maybe there's like a bad x where this is equal to 0. So let's see, is this thing ever equal to 0? That's a good question. So let's see if we can figure that out. Okay, so we're going to do this times this minus this times this. Okay, so that's going to be e to the 3x times negative 3 e to the negative 3x minus 3 e to the 3x times e to the negative 3 x. Okay. Let's see. So when you multiply these terms together, you're going to add the exponents. So we get 3x plus negative 3x, and that will give us 0. So let's write this out. So we have negative 3 e to the 3x minus 3x, and then we have another negative 3 e to the 3x minus 3x. And that's just going to be negative 3 times 1 minus 3 times 1, and we get negative 6. So actually it's always equal to negative 6, and it is never 0. So what we have from this then is that it didn't really matter what this initial condition was. So was it 0 or was it some other number here? So we could put any number here, any value of a, and we could have had any value of these right-hand sides. So any b0, was it b1 and b2? What did we call it? Was it b1 and b2, or it was b0 and b1? So we could have had any b0 and b1 here, and we would have always been able to find a unique solution to c1 and c2 that satisfies those initial conditions. And that's because this determinant is always equal, is always not equal to 0. Okay. So this is like a general idea. It's so important that it's actually, I guess this is somebody's name, so Wronskian. So this is a general technique known as the computing the Wronskian for a set of functions, or for, in this case, it's just 2 functions. So the determinant of the determinant of this matrix, y1, y2, y1 prime, y2 prime, that determinant is known as the Wronskian. So this is the Wronskian. We use W to represent this, this determinant, W of y1, y2. And that's the formula there. But it's always good to just remember it as the determinant. It's much easier to remember than trying to remember this. Okay. So this brings us to a really nice idea that work that we did in showing 2 functions were linearly independent. If those functions happen to be solutions of the same differential equation, then things become really, really nice. All we need to do to determine if they are linearly independent is this Wronskian test. So what is the Wronskian test? So you just take those 2 solutions, you compute their Wronskian just like we did in that previous example. And if it is 0 for all x, then those functions are linearly dependent. And we know this would be a big problem. We wouldn't be able to satisfy our initial conditions if that was the case. However, if the Wronskian is never 0, and this is what we saw in our last example, if it's never 0, and we just need it never 0 for some value of x. So if maybe it's 0 for some value, but we just need it to be non-zero for some value of x. And then in that case, y1 and y2 have to be linearly independent. And it's quite easy to show that if this is ever 0, then these are linearly dependent. Yeah, so that's it. So this is our Wronskian test for linear dependence, linear independence. This will tell us that we have some redundancy, and this tells us that there is no redundancy. Okay, so let's do an example where we use the Wronskian to show that these two solutions of the differential equation are linearly independent. So let's start off with this. So we want to compute their Wronskian. So what is the Wronskian of these two functions? It's going to be y1, y2, y1 prime, y2 prime, and that is equal to what? So y1 is e to the negative x, and y2 is x e to the negative x. Then we take the derivative of this one, and the derivative of this one is, so it's going to be 1 minus x e to the negative x. We already saw this before earlier in the lecture, but that, yeah, that is what you get. You get that. I just simplified it because I don't have a lot of room here. So let's compute this determinant. So we'll do this times this minus this times that. See what we get. So we'll get, so this is going to be, yeah, let's just write it out in full. So this times this minus negative e to the negative x times x e to the negative x. So we'll get 1 minus x times e to the negative 2x. And then we will have plus x e to the negative 2x. And this guy and this guy will cancel. And so what we're left with is just e to the negative 2x, and this is never equal to 0 for all x. We just needed it for some x, but in this case, it's not equal to 0 for all x. Okay. And there's actually a general proof. It's one of the homework exercises. One of the suggested exercises shows that if it's not equal 0 somewhere, then it's not equal to 0 everywhere for the Wronskian. So I think that's exercise 32. So definitely check that one out. Okay, so therefore y1 and y2 are linearly independent by the Wronskian test. Okay. All right, well, let's do the same example, but now we're going to take two functions that are linearly dependent. And it's pretty easy to see that they're linearly dependent because y2 is just 2 times y1, right? So that's obviously going to be linearly dependent. But let's use the Wronskian to show it, because these are both solutions to the same differential equation. So we can use the Wronskian to do this. So what is the Wronskian? Okay, so e to the negative x and 2e to the negative x. And we get this for the derivatives. So we'll have e to the negative x times negative 2e to the negative x minus negative e to the negative x times 2e to the negative x. So this is negative 2e to the negative 2x. And then we have plus 2e to the negative 2x. And that is equal to 0. Okay, so therefore, y1 and y2 are linearly dependent. Okay, so you see how closely related this idea of linear independence and linear dependence is to this Wronskian, and how this Wronskian actually came up when we were trying to use our initial conditions to find the values for C1 and C2. Yeah, so really what ended up happening in this section is we ended up looking at just simple linear systems with 2 equations and 2 variables. And we just used our knowledge from previous classes that linear system will have a guaranteed solution, unique solution, if the determinant of that 2 by 2 matrix is non-zero. So that is the main idea. And that is the end of this section. Thank you for watching.